Hey everyone, so Miss Helen is here, and today we are going to be going over balanced and unbalanced forces so that when you come in, we're ready to get right into Newton's laws of motion. So we will be covering Newton's laws of motion, that is the law of inertia, F equals ma, as well as action-reaction. And these are the actual laws that are written out as they were intended to be, but we'll be covering those when you get to school. Today's focus is going to be on balanced and unbalanced forces. So in order to start, we need to know what a force is. And basically, a force is a push or pull that causes a change in the motion of an object. So it could be any force that causes a change, a push or a pull that can change the way that an object moves, either creates it so that it starts moving, slows it down, speeds it up, or changes its direction. So these are some examples of forces that we don't see happening. So they're not contact forces. You know, if you were to push a shopping cart in a supermarket, that's a contact force. I could see that you are physically pushing that cart. So this gets us to think of other forces that exist on Earth that aren't necessarily just contact forces. So we have gravity right here, which is the force between two objects. We have this girl dropping the basketball, going towards the Earth. We have the moon being pulled towards Earth due to Earth's gravity. Over here, we have electricity or static electric force, which is kind of allowing electrons to pass one object to another, which can create a push or a pull. We also have magnetism, down here, which is another non-contact force. So it can pull any metallic items towards each other or push them away too, as well as friction in the bottom right corner. Friction is the force that opposes motion. It slows things down. So those basketball players' feet, there's friction against the floor and their sneakers. And, you know, basketball sneakers are designed to exert the proper amount of friction. So that just is an overview of what a force is. Now we're going to talk about force as a vector. And basically, a vector is something that we measure both the size and the direction with. So, for example, if we have this kid on a scooter and he pushes on the ground with his foot, and he's going to push that way. So he's going to push behind him. The scooter will move forward. Okay, so he's applying a force behind him. The scooter will go forward, either with a strong or weak amount of force. So it depends on how hard he pushes. If he pushes strong, then the scooter will go further. If he pushes weak, it'll go less far. And it's going in that direction because it's opposite the way he's pushing. So vector gives us both size as well as direction. So we're going to watch a really quick video. It's actually a brain pop video on forces being both size as well as direction.
Man, I can't wait to see what my birthday activity is this year. You're the best robot pal a kid could ever... No. I think I might just answer this letter. Dear Tim and Moby, if forces are invisible, how do we know they exist? And how do they work? Thanks, Caitlin C. Forces are at work all the time, acting on everything around us. We can't see them, but some of their effects are pretty obvious. Like any time an object changes speed or direction. At its most basic, a force is a push or a pull, and it always involves two or more objects. Something providing the push or pull, like Moby, and the thing it affects, like, me. Well, it's never really that simple. Objects usually have lots of forces acting on them at the same time. Each one has a magnitude, the size of the force, and a direction. Put in fancy science terms, we say force is a vector quantity. Like right now, we are pushing in opposite directions. But our forces are in balance, canceling each other out. That's why I'm not moving. The sum of the forces, or net force, is 0. 0 newtons to be precise. That's the unit we use to measure force. It's named after Isaac Newton, the physicist who figured a lot of this stuff out. To get me in motion, you need to exert an unbalanced force on me. That's any push or pull where the net force is not zero.
Also, take a look at the size of these arrows. Notice now how the arrow with 100 newtons is smaller than the arrow with 200 newtons. So the actual size of the arrow does play a part in determining the strength of the force.
I am not getting in that thing. What? You're just trying to distract me, but fine. Right now, there are three main forces accounting for our movement. The engines are pulling the plane forward. There's friction, the resistance the surface puts on anything sliding over it. And drag, which is basically the friction of air molecules. Yeah, you would think the force of the engines must be greater than friction and drag. After all, we're moving forward. But notice how still it feels in here? If the forces were out of balance, we'd feel the push, and we'd be able to observe its effects. Well, we'd see a change in the plane's speed or direction. The combination of these two values is called velocity. We're not speeding up or slowing down, and we're heading in a straight line. So the net force on the plane is zero, same as if we weren't moving at all. We're going to need to accelerate if this hunk of junk is going to get off the ground. In physics, acceleration isn't just speeding up. It's any change in velocity, including speed-ups, slowdowns, and turns. There's a reason you can feel it when a car or a plane accelerates. It means there's an unbalanced force being applied to it and to you. Yep, the plane has to generate enough upward force to overcome gravity. It's a little different than the forces we've talked about so far. Friction, drag, you pushing me, those are all contact forces. They're between objects that are touching. Gravity is a non-contact force. It can affect objects that are separated, like the Earth and this plane. Magnetism and the electrical force are non-contact too. Like all non-contact forces, gravity acts through a field, an invisible area of influence. Fields get weaker the farther out you go from their source. But even way up here, Earth's gravitational field is still plenty strong, which is why I am absolutely not Oh, hi. Yup, the gravitational force is pulling us down, hard. It's opposed by drag, which is resisting our downward motion. The two forces are way unbalanced, that's why we're still accelerating. But the faster we go, the more drag increases. Eventually, those two forces will fall into balance. There we go. Our velocity is steady, which means we've stopped accelerating. So the net force on us is now zero. That's why it doesn't feel like we're falling anymore. More like floating. When we pull our cords, our parachutes will increase drag. So there'll be a sudden, unbalanced force upward. Oof! But as we slow down, drag decreases. Eventually, drag and gravity balance again, and our velocity levels off. Hey, you know what? This was the best birthday present ever. Oh, you.
Okay, so we have our video on forces as a vector. So hopefully that kind of gave you some background knowledge or kind of sparked some of your knowledge about forces. So we'll get back into it. So yes, forces are a vector. They have both size as well as direction. And like other vectors, a force can be represented with an arrow. And as we saw in that video, the size of the arrow and the direction of the arrow do make a difference. So the length or even the width of each arrow represents the strength of the force. So the longer the arrow, the stronger the force. The wider the arrow, the stronger the force. And the way the arrow points represents the direction of the force. So in example 1, we have two forces applied in the same direction. See, they're pointing in the same direction, but force B is stronger than force A because force B is a larger arrow. It's longer. In example 2, two forces are applied in opposite directions. So now they're going against each other, but the forces are equal because force A arrow is the same size as force B. Okay, so we can show these differences using arrows, and the length of the arrow as well as the direction play a part into how we view each force. So now we're going to get into balanced and unbalanced forces. Basically, when you have two or more forces acting on an object, those forces could either be balanced or unbalanced. A balanced force is when we have two or more forces opposite in direction but equal in strength, and they do not cause a change in movement. So over here, we have two forces, and they're pulling on what would be perceived as a central object right in the middle. So we have 5 newtons pulling to the left, 5 newtons pulling to the right. They are opposite in direction, but equal in strength. The arrows are the same length, and it also tells us it's 5 newtons. So this object in the center is not moving. Okay, that kind of goes back to that video where Tim and Moby were both pushing on each other with equal force. They would just stay there pushing off of each other until a change in the force happened. So if we have balanced forces on an object, if they are not moving, they're not going to start moving. And if they're balanced forces, they'll keep doing whatever it is they were doing. So if you have balanced objects or balanced forces on an object in motion, it will not speed up, it will not slow down, it will keep moving as it was intended to. So that's kind of a cool thing about balanced versus unbalanced forces. Or rather, balanced forces. Balanced forces cause no change in motion, even if it was already in motion. And then we have unbalanced forces. They are unequal. Okay, so they're opposite in motion and they are unequal in strength. And they will always cause a change in the direction or speed of an object. So over here we have two forces pushing on an object over here. The force pushing to the right is with 5 newtons. The force pushing to the left is with 10 newtons. So the force with 10 newtons is going to win over the force with 5 newtons. So how will this object end up moving? It's going to move with 5 newtons to the left because 10 is bigger than 5. You do 10 minus 5, there's 5 newtons left over, and it's going to go to the left because that's how the bigger force was pushing. Down here, we have two forces pulling on different objects. We have 5 newtons pulling to the left, 10 newtons pulling to the right. If we kind of do 10 minus 5, we have 5 newtons left over, and it's going to go to the right because that's the direction of the larger arrow. Okay, so basically when we are looking at unbalanced forces, they always cause a change. The combined force is equal to the difference, so difference means subtract, between the two forces and is exerted in the direction of the larger force. All right, so at this point, we have learned all we need to help out for Newton's first law, which is what we're going to learn when we get back to school. So after you complete watching this video, you should be doing the exit pass that is found on Classroom. And I'll see you guys when you get back to school. Adios.